So welcome to Friday. Next week we have spring break. So this is our last class leading up before our break next week. So no classes next week, but we have a couple quick announcements leading up to what's happening next week. So first of all, we should be able to finish the grading and uploading of the midterm part. So those will be put up onto Canvas, if not this weekend, next week. Second part too is we have sort of a play-by-play explanation that I'm preparing for each question. So if you have questions about how to accomplish different parts of the midterm questions, go check up on Canvas. We'll have those posted in the midterm section. So that'll be over the course of next week. As we transition, today we're going to finish off the last discussion of kinetics. This is the physical portion of the course. So in that, what we're doing is we're going to be transitioning now from sort of our main discussion of physical chemistry and switching over to organic chemistry. As we get ready for that, there's a little bit of homework you guys have to do next week. So we have some material we want you to view. There will be a slide or a link that will be available up next week. This will be on the Canvas page. What you have to do is go to this link, watch a video, and what this is doing is we're preparing actually some material here for you guys to help teach this concept. If you participate in this, there's a study attached to the video, so the video is important to class regardless. We want you to watch the video so that you come to class ready on Monday to talk about how to do IUPAC naming. So this is naming of organic molecules in a systematic way. So make sure you do this next week. It's just a sort of a 10-15 minute video primer. After that though, if you wish to participate in a survey talking about how this video worked or your experience with it, you'll be given a 1% bonus mark on your final. So this is completely voluntary, but it's a way for you to pick up a bonus mark, okay? We really appreciate you guys to sort of work into it. If you're interested, this is the QR code. Again, we will post this link onto Canvas. These slides will also be uploaded, so you don't have to grab it right now. But if you're interested, this is where it will be. Again, the links will be available on the 21st to 27th. That is your window to participate in the survey. The videos will be available long after this. You'll be able to see it as much as you want after. But this survey specifically opens and closes in this time. So that's your time to do this point. But again, thing to isolate, thing to make sure that you do. That video is really important to do before you come to class on Monday, at least as a primer to get ready for how we talk about IUPAC naming, okay? So where we left off last time was we were talking about the steady state approximation. We now are talking about multi-step reactions and solving for the rate equation for these multi-step reactions. Remember, in a multi-step reaction, we're going to consider just two basic cases. So in the first one, any multi-step reaction for right now is going to be something where we have an overall reaction, let's say A plus B, goes to C. The overall reaction is not an expression of how we got there. It's not an expression of the specific mechanism. The mechanism, we're going to consider cases where there is 1, 2 steps, and in a general sense, it's going to look something like in the first step, let's say this is A plus B in equilibrium with an intermediate. In the second step, intermediate goes on to product. Now the specific organization of what shows up where, how many intermediates you have, that can change. There's different organizations of these different species, but they'll all have the general point where there's a first step, which we could potentially consider as an equilibrium, and the second step where we have our rate determining, or sorry, not rate determining, our product forming step. This is where we break this down and we can say there's K1, K minus 1, and K2. We have 3 rate constants, and sorry, I'll clean up my arrows here. What I mean is K1 is the forward rate constant, the microscopic rate constant of that first part forming product. K minus 1, microscopic rate constant, intermediate going back to this. This is how we define an equilibrium as 2 elementary steps, one forward, one back. And then finally we have our formation of our product, our K2. So this is the generic picture we discussed. We're not talking anything about which of these steps may be rate determining. This is just the playground that we're going to talk about. We talked about 2 extreme cases. First step being rate determining, second step being rate determining. if step 1 is what we call the rate determining step, what can we do, or what assumption can we make? What's the big thing that makes that easy? If we say the first step is rate determining, what does the overall rate equation look like? Or what's driving the bus in terms of control of this reaction? Just the first step. It's only really little k1 is really controlling everything. So what that would look like, if the first step is rate determining, we can look at the coordinate plot. What we're saying there is it's something like a big first step, small second step. It has something like that mentally, where there's a large delta G double dagger of activation in that first step. It also means that this whole complex equilibrium reduces so that overall d product dt is equal to, or just rate, is equal to really k1 times whatever's in this first step. Here, that's A and B. It's only that first elementary step that's really controlling every other part of this. Now, that's the first simplification we can do, but we need to know the first step is rate determining to make that jump. The general case, the overall general one, is still these 3 steps. They still exist. They have to happen. But rate determining, we've made a call about which one is rate determining here. All right, I'm going to copy this, and we're going to do the other case. Oops. So now, if step number 2 is the rate determining step, that's we're saying this one is driving the equation. Truly there, what happens is the overall rate of reaction is now proportional, or really only equal to, the concentration of our intermediate times K2. It's this step right here that's controlling the overall process. Again, that's the same thing as we said about the first. It's just that simple. The problem here is that the intermediate is actually the one that's controlling the rate, and that's not something that we necessarily know its concentration. We didn't add it to the reaction, so we don't know what it is a priori. So we have to come up with a new expression that it talks about this. And what we talked about before is the expression we can do if the first step, if the second step is rate determining, we can make an assumption that we're going to say that first equation, that is in equilibrium, and it always stays in equilibrium. This is the pre-equilibrium approximation. What we say here is that this can be approximated where really capital K, the equilibrium constant for that first step, which is equal to concentration intermediate over, in this case, product over starting materials, A times B, which is also equal to K1, K minus 1. The ratio of the 2 microscopic rate constants is also equal to the ratio of products over starting materials. And this now has a term, the intermediate, that we can now solve for other pieces of the reaction we might know. The K1, the K minus 1, A and B. And we can use that to rearrange to sub into this intermediate concentration. It's an algebraic rearrangement to solve for that component. So those are 2 extreme cases, but in both of them, the thing I want to underscore, you have to know if first step is rate limiting, here's how you simplify. Second time, if the second step is rate limiting, here is how you simplify. The last thing we discussed last time was what was called the steady state approximation. We called this SSA. The difference here, this is not dissimilar to any of the other ones. This is just a more general approach to talk about how do you get to a rate equation. The steady state approximation makes no assumptions about which one is rate limiting or not. All you're saying is, I have a complex series of equilibria, I have a complex series of different steps, and the only thing I'm making when I say steady state approximation, I say that the change in the intermediate concentration over time is equal to 0. I'm not saying that the concentration of that intermediate is 0. I'm saying that it stays constant. Or most of the part of the reaction where it obeys this rule, the middle part of the chemistry, this is true. So if that is true, again, it allows us to come up with another expression, this time determined at what is changing the intermediate concentration. We have to come up with an expression that talks about how that intermediate is formed, so that's a positive something, and how it is used up, a negative something. Yeah?
It's like created and then used up. You said
like effectively, we know that it has to be there. It is some value. We're just saying that it is formed as fast as it is used up, so it's d intermediate dt equals 0. Right, the overall change is 0. That's true. Yep. So if this is the case, it just gives us a way of expressing this. So in this example, what we would do to solve for this part, I am forming it according to K1. The first step is A times B. I'm using it up, the backward rate constant here, K minus 1, times the intermediate. And I'm using it up according to the second step here, K2 intermediate. Now, for simple systems like this, the number of terms you have in this one here will be determined by the number of individual steps that either make or use up that intermediate. We have 3 individual equations, so we should have 3 individual terms, a formation and 2 consumptions, because there's only one way to make it, 2 ways to use it up. And from here, once again, we go through, we algebraically solve for intermediate concentration, and we will put that back into the overall rate constant. It's still the same thing as we did in our second step. We said the rate here is still really determined by that final step. It's d product dt, which has this intermediate part to it that we're going to come back and sub into it. The answer for this, the steady state approximation, is what we would call the general solution. We're not making a statement about who is slow or who is fast. We're just saying that based on the steps that we have, where those intermediates are, where they're positioned in our mechanism, we get a single formula. And that formula doesn't say anything about first step is slow or second step is slow. It is just the mathematical expression overall. Now what I've done is I went through and I broke down what we were saying last time. The steady state approximation, if you look at just the overall equation for the steady state approximation, it is possible to say, all right, given the steady state approximation, now I'm going to assume the first step is slow. That has something to do, or you're saying something about the size of K1 once you make that statement. Remember, statements like first step is slow or second step is slow is telling you something about a magnitude of a rate constant. So back to our overall picture. If we said first step is slow, and I'm drawing this in terms of a equation like this, or sorry, a diagram of free energy versus our coordinate. First step is slow. What does that look like? Big hump first or little hump first? Yeah, first step is slow. We're going to have a large barrier and then a small barrier. Really what we're saying is it's this one right here, the delta G double dagger, is the one that's really controlling this overall reaction. What do we mean about the relative Ks? If K, well, here on this diagram, if I'm trying to sort of break it down, I could say that K1 is this way. Going from here to here, this is where we extract our K1 value. The K1 is informed based on moving from starting material to that intermediate, the forward direction of this process. Going from here back, that's what would be our K minus 1. It's going back over that barrier, back to starting material. And then finally, K2 is this jump right here. So the barrier heights, where they are, tell us something about magnitude. So based on our statement, we said the big jump is up front. That's our first step is slow. Which value of K is smallest? Both based on this picture and what you know about what we said. K1, K minus 1, or K2? Which one should be smallest if the first step is slow? Well, smallest. Remember, small means what? Fast rate or slow rate? Slow. First step is slow, so which is the slowest step? K1, K minus 1, or K2? Yeah, K2 definitely is out, right? K1 and K minus 1 might be very, very small, but probably K1, that first point, is the thing that's really, really controlling it. That's another expression, what we said about the simplification we did back here, right? If first step is slow, K1 is driving the bus, it's the smallest rate constant, it's the one that's driving the reaction. Okay, let's do that same map now for the other case. If the second step is slow, what does our diagram look like? Yeah, little, and then a bigger one, right? So what we have here, again, if we break these pieces out, it's this second step here, that's my delta G double dagger. This step here, that's my K1. Going back this way, that's my K minus 1. And on to products over this one, That's where my K2 comes from. Which value of K is your small one here? K1, K minus 1, or K2? K2. So this relative sizes that you are going to run into here are proportional, basically. Big barrier height, little K value. Big barrier height, long amount of time. Small K, small rate, right? So this is what it looks like for our second step being slow. Based on these values, the sizes of K's that are happening here, you can look back at the steady state rate equation and do some simplifications of the denominator that you will get, which lead you to the same answers you get from either our pre-equilibrium assumption or our first step being slow assumption. So I've gone through and done a longhand algebraic explanation of that one. I've added it as a video to last class. So if you want to look at that part in more detail, please go back and review that. That part is online right now. So this is our sort of the different parameters we have. We have the steady state approximation. This is the general solution to a multi-step reaction, and it mainly applies during this heart-cut middle part of the reaction where we're saying that the concentration of the intermediate remains relatively constant. From that, the thing that I want you guys to practice, and we'll have the longhand derivation of each of these. We have those 4 steps for how we get to the steady state approximation, right? 1, 2, 3, 4. Those steps stay constant. Their application and the equations you solve will be different depending on the mechanism. So in the next couple slides, we provide you with the same overall reaction. A plus B gives you product in C. Given that, we say this is a hypothetical mechanism that explains or obeys that overall reaction. It's one arrangement of these tools. So here, A is in equilibrium with our intermediate. Then the intermediate comes together with our B to make our product, plus some byproduct. That's how this arrangement goes. Based on that, if you do the steady state approximation, walk all the way through it, this is the rate equation that you solve. You're going to have a particular form where you have some grouping of rate constants and some grouping of concentrations. That is going to be unique to this particular pattern. So notice here, one thing goes in, one thing comes out. B is involved in the second step. Product has, there's 2 different species here in the product. That is the arrangement of this mechanism. And notice that this term here is relatively simple. We just have A and B in the numerator, B in the denominator, and we have this sort of 1 plus form again. If we go through and we just change it just ever so slightly, notice here, same overall mechanism. But now the first step, 2 species are coming together to make a single intermediate. We've just changed how this reaction happens, just slightly. B is now involved in the first step. It's involved in the equilibrium. Because of that, the arrangement of where things happen, the math is going to come out different, and you end up with a slightly different rate equation. If you go through and solve it, now notice there's no B in the denominator for this one, just because B is involved in that first step, it's not in the second one. Which means that B is going to have a different behavior mathematically. As I change the concentration of B for this equation compared to the first, it'll have a different impact in the overall rate of the reaction. Likewise, if we go through one more time, A produces 2 things, and then they come together again. This is just another hypothetical riffing of these materials. We get a slightly more complicated rate equation. Once again, there's now these terms where C and B, their concentrations show up in the denominator. This is now a reaction which will actually be inhibited by this byproduct. C is actually going to start to slow the reaction down because it's in the denominator of this thing. It'll decrease the size of the rate constant. So the thing I want you guys to practice through, given these 3 individual mechanisms, 1, 2, and 3, practice the steady state rate equation procedure. It's those 4 steps algebraically. You should get these answers. Try them yourself once. There's a longhand step-by-step one that I will post up over reading week. You guys should know how to do these kinds of things coming up for midterm 2. Okay? So again, this is just practice through it. Now, why do we care about this? The specific rate equation that we solve can tell you which one of those 3 mechanisms is correct. So what we just did is said I have some reaction, but I don't know the mechanism. I proposed 3 possibles. Based on proposing these 3 possibles, I have 3 different equations that tell me how rate will change as I change other stuff. So what about this case? You do an initial kinetic experiment. You have 1, 2, 3 runs. If this reaction proceeds according to the two-step mechanism showed down here, notice this is just a single reaction. We're not even getting as complicated as equilibria yet. Which is the rate determining step? Which is the right mechanism? Take a second, turn to the person next to you. How do you work this problem? How do you use this different piece of information to work this out? Okay. So give me a strategy. We're mixing a bunch of different information to teach you something about this reaction. First of all, the table we gave you at the top, what do you use that thing for? What is that an expression of, or what do we call that kind of series of experiments? It is, yeah, this is your method of initial rates. What are we doing when we do the method of initial rates? What are we solving? Well, okay, yeah, that's one part. What else? Order, exactly. So, if I take these two experiments, I changed my butyl bromide. I do not change my Ki. What happened to the rate? So here, this is 2 times. Nothing happened here. This one is 2 times, right? What does that mean? First order in this species. So far what we've said, it's like playing Sudoku. Rate is equal to K times at least this stuff, CH3, 3, CBr. And we know that's at least first order. So we have a piece of the experimentally determined rate equation. All right, now we do the second one. If I take the second step, I'm going to compare these two. I don't change this one. I double this. What happened to the rate? Nothing. What does that mean about the rate equation? First order, zero order? So we know now this system, oh man, I really need the break too. This system, the overall reaction has 2 components. From that overall reaction with 2 components, only one of them shows up in my rate equation. Okay, so we know that the experimentally determined rate equation really is rate equals K times this one component, only this. If that's true, which one of these 2 steps has to be rate determining? First step or second step? First. Why? Does the second step have that as the starting material? This is in the second step. It doesn't care what happens to this concentration, does not make it go faster. This is, you are driving your Ferrari, but you are stuck on campus. This is your slow step. Adding concentration here, Ki, will not change the rate because it's after the rate determining step. It is 0 order. This here will show up as 0 order only if that first step is rate determining. So that's how this part works. We bridge together experimentally determined rate equations and then the mechanism that matches that particular reality. So this would say our initial rate experiment would be in support of the case where a mechanism where first step is slow. So this is our actual true experiment. This is one I've actually run many, many, many times. It's known as a SN1 reaction. Does anybody know or heard of what an SN1 reaction is? Oh, I can't wait till organic chemistry. It's a substitution reaction where we actually break into 2 pieces, but we will be using this one over again. Okay, so that's how you put the pieces together. The reason that we use our experimental rate equations is because we map them against theoretical rate equations, mechanisms, and we use the 2 to validate them. So the next level of complexity we do is enzymes or catalysts. Remember, an intermediate is something that is formed and then used up. It shows up only as the reaction is produced. So it is formed as a product in a starting material somewhere else. A catalyst has sort of the opposite disposition. Catalysts need to be there at the start, but they're returned at the end. And usually we display in the overall reaction, catalysts show up above the arrows. They're not a starting material. They're not a product. They show up as a needed component. It's like a solvent. It's something else that the reaction will not occur without. So the difference is they have this kind of disposition. Starting material and product both show it, so they need it at the start and they come back at the end. And then also, again, that's how we weigh that against intermediates, which form and then go away. Okay? Enzymes are the most common catalysts we ever interacted with. Enzymes are what make biological processes happen at room temperature and pressure. Now, the most important thing is an enzyme does not make a reaction faster by changing which product you make. What it does is it changes the path. Catalysts work not by saying that I will make the products more stable. It's not by taking the starting material and making them more reactive. What it does is it creates a new path or bridge through what would be otherwise an impossible delta G double dagger. So what we do is, again, if you think about this in terms of topology or sort of mapping, if I'm trying to get from here to North Van, how might you do that today? What is the mechanism that you would possibly do if you were on foot? That is all you have. How do you get from here to North Van? I said on foot, but okay. But even then, even if you took a bus, what route would you take to get from here by bus to North Van? Yeah, through the bridge, over Lions Gate, sit on traffic because it's one way the whole time, and then eventually make it over there, and then 3 hours later you're in North Van, right? That takes a very long time with a very high activation barrier. What if now you had a catalyst, a boat that you could get on Red Beach at with your clothes on? Would you be faster if you were able to take a boat? You have a new route that's available to you, which means you can actually traverse a whole new ground. That's what we're doing here, is we're providing a new path where that path often has new intermediates, and what that means is the barrier gets smaller. Catalysts do not make reactions faster by changing delta G naught. Notice here, delta G naught remains constant even with and without the catalyst. What changes is how high your barrier has to be, which means your rate constant gets faster. Yes?
So in a multi-step process, only the delta G double dagger of the rate determining step matters, right?
That's true. The highest barrier, your delta G double dagger of your big jump, is the rate determining one, being it first or second.
So it's not like in the first step you use up free energy at all?
Yeah. No, what we do is we say that there's a conservation of energy, right? So even if the first step is a large barrier, you had enough energy to get over that, so you will continue on to products from there. It's not that the reaction gets tired at that point. We assume that there's enough energy to continue through it if you made it through that first pass. Yeah, that's right. So really the concept here is catalysts give you this tunneling. It gives you a new path or a bridge or something else to get through by a new path. But more importantly, the way that they impact rate is not by changing stability of different pieces. What it does is it gives you this overall new delta G double dagger through here. And again, how this usually happens is you would take what normally would be this one ridiculously high barrier and you break it into a lot of individual pieces. You create intermediates which are overall more stable than the overall path would be. So as a result of that, the mechanism gets a little bit more complex. You've got this handoff now, instead of having starting material becoming product. Starting material will usually interact with catalyst. Catalyst may turn to something else, and then that turns to something else, and then eventually that material releases the catalyst again. So it's like going through a little bit of molecular origami where the catalyst is holding on to it and manipulating that change. So from the perspective of kinetics, this makes things just a little bit more complex. In general, Michaelis-Menten kinetics is what we talk about when we talk about enzyme kinetics. This will bridge over to anything you do in biology, definitely over things where you look into anything with medicine. Enzyme kinetics, defined by Michaelis-Menten, says it follows an overall path which looks a lot like what we just talked about. We can take any enzyme reaction where starting material becomes product, S, our substrate, becomes product, the red guy, and it goes by which it actually hooks onto our enzyme. It makes what's called the enzyme-substrate complex. Enzyme-substrate complex goes on to product and regenerates your enzyme. So notice the enzyme substrate complex is the intermediate, what we just talked through. It still has a first step, which is in equilibrium, K1, K minus 1. And we have our product forming step, K2. In biology, they call it Kcat. So it has the same 3 overall steps that we're used to. The only thing that gets more complex now is that we have this enzyme coming in and enzyme coming out. The cycle we're talking here is not about a linear process anymore. Now the enzyme is formed and goes away. In fact, you can think of it this way, where the enzyme is going to react reversibly with our substrate. That forms our enzyme substrate complex, which then regenerates enzyme and kicks out product. So we have this little motor, a cycle of enzyme going from enzyme, enzyme substrate, enzyme substrate, around and around. And feeding into it on one side is our substrate going in, spitting out the other side, product coming out. This is the engine in the middle that runs this whole process. So the kinetics are very similar to what we talked about before. The steady state approximation can be applied here in the same way as before. The difference now is since we have this enzyme, we have to make it a little bit more complicated in terms of the math. So, sorry, boop, no, no, there we go. In general, one of the things that Michaelis-Menten kinetics makes an assumption, a lot of the times that first step in most enzyme catalyzed reactions is going to be a fast pre-equilibria. The second step is your product determining step. That is generally, on most cases, your slow step. So most of them follow this general case where we use something like the steady state approximation in that first step. So what we're going to do is apply the steady state approximation, assuming these 2 parts, and we're going to do it just like we did before, the same 4 steps. Step 1, we draw the rate of product formation based on this second step. That's our d product dt is equal to Kcat times enzyme substrate, right? It's just this particular one elementary step. Step 2, we define change in our intermediate. Intermediate now is just our ES. Versus time, we say that that is equal to 0. That's an expression of our steady state approximation. And like before, we have 1, 2, 3 steps, so we have 1, 2, 3 terms. The mechanism is a little more complex. We now have both substrate, enzyme, enzyme substrate, and enzyme substrate. So good, it's usually following the same path. Everything's feeling great, except the one thing that makes this more complicated is we actually have 2 unknowns in this profile. We know the substrate concentration. That's how much stuff we gave. That's the fuel for the reaction. The enzyme substrate, that's the intermediate we're trying to solve. That was why we set up the steady state approximation to do. The problem is this E is not the enzyme you started out with. Remember, when you start this reaction, you can think of it as I take my enzyme, that's a bucket of enzyme protein. I take my substrate, and I'm going to mix them together. As soon as I do that, if you look at this process here, some of that enzyme, some of the overall E shown in green, will bind to make my enzyme substrate complex. The total amount of enzyme I throw in, whatever I start before the reaction starts, gets distributed between free enzyme in green and purple, the intermediate. It's split between the 2. So the thing that makes this more complex is this value. This is what we call our free enzyme. I can't spell today. Or free catalyst. And that's not equivalent to the total catalyst we started out with. So we're back to saying, okay, I have a value or term that doesn't relate immediately back to something I started my experiment with. So I have to do one more thing to make this possible. We need to add what's called the mass balance equation. The total amount of enzyme I started out with, the total catalyst, is equal to the sum of however much is in those 2 states. The enzyme can either exist as free enzyme, E, or bound enzyme, enzyme substrate. The enzyme total, this is what I started my experiment with. That's the thing I know. So now what I have is a new term, this mass balance equation, which allows me to relate the new unknown, free enzyme, to these two. It allows me to re-express my steady state equation where the only unknown is my intermediate now. So I plug in this value here back into my steady state approximation. That's this one here. I've replaced this. This used to be my E term, the free enzyme. So it gets a little more complicated. But now we still have that is equal to 0. We rearrange it. We solve in terms of our enzyme substrate to give us our final term. So once again, we have a new expression now in terms of only two species that we started this reaction out with. We know our substrate. We know our total enzyme, our total catalyst. Those are species we started the reaction with. So this is constant now. Now we have is this overall process, and we're saying that for the steady state approximation, this is this term we can sub in. That's our step 3 from our previous sort of series of 4. Last step is to put it back into our overall product forming step. The product forming step was our second step times intermediate. We now have a new term for this, so we drop that term in. That's this whole overall term over here. That is the Michaelis-Menten steady state approximation. The good news is all enzymes follow this pathway. This is not something we necessarily have to rederive. All enzymes follow this one, so this becomes a common equation, known as the Michaelis-Menten equation, describing how all enzymes behave. As long as one substrate goes in and works with an enzyme, they all follow this pathway. Things do get more complex if multiple substrates get brought in, but the nice thing is most enzymes obey this law, so this becomes a constant. One thing you'll see up here in the top corner, this is how we as organic chemists would express that mechanism. The sort of forward, backward, and product forming step, that's the steady state approximation. And the only thing that's different is we call K1 and K minus 1, that's the first equilibrium. K cat, that's our K2. What you'll often see though in terms of in certain biology texts, what they'll do is rearrange it into this form. What they're doing is rearranging certain constants because they care about certain constants as sort of binding constants or again rate constants that are important for reactions. Oh man. So what happens now is by rearranging this, we come up with two new terms. If I take this term here, and all I'm doing is algebraically going through, grouping terms together, and I define what we call Km. This is the Michaelis-Menten constant, the Km value. It is just expressed as the forward and backward rate constants plus K cat. So all we're doing is taking this here and then rearranging it to give us this overall form. We define this term Km because Km is a value which actually determines how tightly substrate is binding onto a species. Again, the only thing that matters here, you should know how to make this kind of an approach. How do you take the steady state approximation to draw this? And you will be given this value here. You do not need to derive between these two. Yep.
The Km isn't related to equilibrium.
No, Km is not an equilibrium constant. It is a grouping of little k's specific to an enzymatic pathway. That's why it's different. It's capital Km is still just a binding constant, not specifically just that only equilibrium constant. It is defined as this ratio of constants. Yep. Again, most important, can you algebraically get here? Once you have this, how might you interpret it? So let me give you an example. Once we derive it out like this is an expression we can do. One further point, biology can actually redo this, and we can define what's called Vmax. Vmax is the maximum velocity of the reaction. This is as fast as it could possibly go. If you gave it all the substrate in the world, given a certain amount of catalyst, it can only go so fast. That's the point where it's turning over and it's cranking at full speed. At some point, if you give it more substrate, if the enzyme concentration does not change, it will go absolutely no faster. We have saturated the enzyme, and this is the limit of how this system will move. So this is an important physical parameter to understand that, look, certain enzymes, if their Vmax value is very, very low, it doesn't matter how much more food you give it, the system will never move any faster. Versus there's other enzymes where their Vmax is exceptionally high, the enzyme turns over very, very, very quickly. So it's an expression of how useful this enzyme might be. But once we're in this form, you can look at two different extremes. Look at the denominator. If we look at that system, what happens to that form if the substrate concentration is very small? How might the denominator simplify if concentration substrate is really low? So the denominator currently is Km plus substrate. But if substrate is really, really, really small, I could say that equals approximately what? If substrate is really little, yeah, just Km. If this value is really, really small, the denominator, instead of being Km plus substrate, is just Km. What about the other extreme? If substrate is really huge, what happens to this denominator? If substrate is very, 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 very large, instead of being Km plus substrate, what does it kind of look like now? Yeah, substrate. If Km is really, really, if substrate is really, really large, it's just equal to substrate. So you have these two extreme possibilities. If substrate is very, very, very large, the denominator is basically just substrate. If it's just substrate, that whole term, Vmax over substrate, reduces. The rate of product formation is just Vmax. That's an expression to say, at some point, giving more substrate to the system, it was zero order in substrate. It will not go any faster. At the other extreme, if we take this system and we starve it for substrate, it is hurting to look for substrate. That means just a little more substrate and it will go just that much faster. In fact, it is first order in substrate. If substrate is very small, this denominator is just Km, so this is what the term looks like. These are the two simplifications that are possible from this Michaelis-Menten equation. So again, Michaelis-Menten equation is the general overall, and we have two conditions. High substrate, where it's basically just Vmax, changing substrate doesn't help anything. And we have low substrate, the case where if I change substrate, it is a first order relationship between substrate and rate. This is where you might have seen this plot. This is what's called a Michaelis-Menten plot. What we do here is we're plotting not concentration time. This is not what we're showing here. What we're showing here is rate, velocity of the reaction, against substrate concentration. So we have the rate here, which is our product over time, and we have our substrate concentration. We're saying, how does the rate change? There's two regimes. Down here where it's low, we have the first order process. Where the substrate concentration is very low, we have, if we double substrate, we double rate. That's the case that looks like this one here. Under low substrate concentrations, doubling substrate doubles rate. At high concentration, we are at Vmax. If I increase the substrate concentration, adding more substrate, making this bigger, the rate stays constant. It does not change. It is zero order in substrate over here. Just stretching. I know it's riveting stuff. So what I'm trying to do is bring together these two concepts. Steady state approximation is a mathematical representation for these complex equilibria. What we do and why we pull it off, so if you've been in biochemistry, have you guys heard of the Michaelis-Menten constant, Vmax, Km, yes? Calculus? What are you doing that in calculus for? True enough. The point I'm trying to make here is that right now, these are handed over as, oh, Km means this value. Vmax is this value. They come out of these two different perspectives. If you starve the system of substrate, you're at one part. If you add extra substrate, you're in the other part, okay? So this is the overall process here. The last thing we're going to talk about, and we'll only touch on this briefly, we will finish up this concept after the break. We talked about making reaction faster by adding a catalyst. But there's one other thing we can do, is we can actually change the value or magnitude of K without changing the mechanism. This is heating up a reaction. If I heat up a reaction, if I change the reaction by changing K, that's the other way I can do this. So we're not saying we take a whole new thing, we're not changing the pathway, we're just making the reaction faster. So to do this, we affect it by temperature, and we use what's called the Arrhenius equation. So what happens here, our dude Arrhenius came up with this relationship. He measured the rate constant K for a variety of different experiments, and what he found is there's a relationship that the K value for any system, even without changing the mechanism, the K would change according to the equation, A, what he called his Arrhenius parameter. I know he's super humble. Exponent, or E, raised to the power of minus EA over RT. EA is what he called, so these guys are ones you know. This is your rate constant, this is your temperature, and this is your universal gas constant. A and E are the new parameters he brought up. A is what he called the Arrhenius parameter, and EA was the activation energy. Now, the important thing here, A changed what he called his frequency factor. What this was is he noticed different reactions had different A values. It was a property which was specific to how a reaction was occurring. So he had to add this factor. It changes with different chemistries. And that's all about the shape and geometry of the transition state, how that transition state works. The EA value, think about that as related to our delta G double dagger. It is not the same numerical value. It's the same concept, though. It's still your speed bump. So he was able to recognize that, look, bigger speed bumps are going to need more temperature to get over, but we also have this other factor A. So these are the two parameters you had to solve. What he did is he said, okay, I have, again, this expression. I have my K and my temperature. If I measure K and temperature, or K at different temperatures, I can extract these constants for any experiment. So this is back to using this as a graph, as a linear best fit. By taking that overall expression at the top, by dividing, take the logarithm of both, you now have something that's in the form of y equals mx plus b, just like we've done for Van Hoff plots, just like we've done for the other sort of first order profiles. So the logarithm of little k against 1 over t as our x value, those are my y and x parameters. My slope is my negative EA over r, that's your activation, and then your intercept is your ln A. Plotting these two gives you a straight line. So that's the useful part of this, is that in this form, this ln k minus EA to 1 over t ln b, you have the ability to extract these values the same we did with Van Hoff or the same way we did with first order rate equations. So last step, for this guy here, if I gave you this plot versus that plot, which one of these has a smaller magnitude of your EA value, A or B? And where do you look to see it? Take a second, talkity talk. I want to finish strong. Which one definitely is the right answer here? Okay, for consensus, everybody all together. Answer is? B. Awesome, good job. It is B. The smaller slope is proportional to EA. That's how this part goes. Okay, let's break there. We'll pick up and do the last part, last calculation, and then we will kick off with organic. Have a great break, guys. I'll see you guys next week, or 2 weeks.